Okay, so hello and welcome back. So the next thing that we have over here is the distance between 2 points. And of course in two-dimensional space we have the distance formula, which was basically this was called the distance formula in 2D space, or basically you can say on a plane, on a 2D plane. And the formula that we had for that kind of situation was basically AB. For example, the distance between 2 points AB is going to be equal to the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. So this was the distance formula that we used for basically for the distance between 2 points A, x comma y, x1, y1 for example, and the point B, for example, x2, y2. So now this is in 2D space. Now in 3D space, the formula is of course going to be a little bit different, because you have basically 2 points, for example P, x1, for example y1, z1, and you have another point, for example Q, and the coordinates of that point would be x2, y2 and z2. So since that is the case, we have to make some changes to this formula. Or basically we need to see how we can find the distance of these 2 points in 3D space. So now how we can figure that out is that you can say that let these 2 points be 2 points referred to a system of rectangular axes OX, OY and OZ. Be 2 points referred to a system of rectangular axes, rectangular axes OX, OY and OZ. So be 2 points referred to a system of rectangular axes OX, OY and OZ, meaning that these 2 points exist in 3-dimensional space, meaning that you have basically these axes over here. You have these axes over here, something like this, and this is the x-axis, this is the z-axis, and this is the y-axis. And then the 2 points are basically, and this is point O, so this is OX, OY and OZ. And through the point P and Q, you want to draw planes parallel to the coordinate plane so as to form a rectangular parallelepiped with one diagonal PQ. So basically, I will write down this sentence, and then we will break it down to understand it, and then we will move on from there. So through the points P and Q, draw planes parallel to coordinate planes. Draw planes parallel to the coordinate planes so as to form a rectangular parallelepiped, so as to form a rectangular parallelepiped with one diagonal PQ, Okay, so a parallelepiped is basically a three-dimensional figure in three-dimensional space, of course, in which all the six faces of that figure are parallelograms. And of course you know that for example, when we talk about a parallelogram, we say that this is a parallelogram if basically if this is a parallelogram and I think that the word parallelogram has to be written this way. I think parallelogram, okay. So parallelogram, and in order for a geometric figure to be a parallelogram, basically all the two pairs of opposite sides have to be parallel, meaning that this has to be parallel to this one and this has to be parallel to this one. And so if these two are parallel and these two are parallel, then this geometric figure is called a parallelogram. And of course so by the same logic, basically, or by the same condition, this is also a parallelogram. This is also a parallelogram, and you can see that over here the angles are 90 degrees. So this is also a parallelogram, which is, well, of course, incidentally, it's a rectangle. And also this would be a parallelogram. This is also a parallelogram. This side is parallel to this side, and this side is parallel to this side. So this is also a parallelogram, which is incidentally, of course, a cube as well. And I think there is a few more things over here, like I don't remember those names or those figures, like the trapezoid. I think if there is a trapezoid, there is a special case as well, where we don't really need to talk about those things, but it does suffice to say that these are all parallelograms. Now, if you have, for example, from this you can create a cuboid. So a cuboid would basically be something like this. Basically, if you put 6 of these together, you will get a cuboid. And if you put 6 of these together, you will get a cube. Of course, this is a square. This is a square over here. This is a square. but then this will be a cube. This over here will be a cube. So from this you can from 6 of these, if you put together, you can create a cube. 6 of these together, if you put together, you can create a rectangle. And 6 of these, if you put together, you can create a parallelogram. And I suppose you can create a parallelepiped. Now a parallelepiped Now a parallelepiped is of course something like this, meaning that if you put exactly that together with something like that, I suppose you will get a parallelepiped. So then if you connect these points together, you will get a parallelepiped. So that is a parallelepiped. Now, so this is basically called a parallelepiped. This is called a rectangle. This is called a cuboid. But well, this is also a parallelepiped because all the 6 faces are rectangles. This is also a parallelepiped because all the 6 faces are rectangles. So these are all parallelepipeds, and these are of course all parallelograms. But then there are special cases of a parallelogram that becomes, for example, a rectangle. There is a special case of a parallelogram that becomes a square, and so on and so forth. So now a parallelepiped is basically something like this. Is basically something in this category is called a parallelepiped. So now the sentence over here that we have is through the points P and Q. Now suppose that you have 2 points P and Q over here. Draw planes parallel to the coordinate planes, meaning that the YZ plane, the XZ plane, and the XY plane, 3 planes parallel to these 3 planes, or well, six of them, each 2 of them would be parallel to one axis, to one plane, so as to form a rectangular parallelepiped with one diagonal PQ. So now if I draw this over here, what I will get is basically a parallelepiped, something like this. And well, of course, as you can see, for example, as you can see, this face up here and this face down here are parallel to the XY plane. These 2 faces are parallel to the XZ plane, and the face on the back and the face on the front are parallel to the YZ plane. So that's basically what we wanted to do. And the 2 points that we were looking for, P and Q, are supposed to be in 2D space, not on one single plane, because the whole goal of this whatever it is that we are doing over here is that we want to find the distance between 2 points in 3D space, meaning that the 2 points have to be on basically on 2 different planes at least. So what that means is that I'm going to take the point P, I'm going to take this point as P, and I'm going to take this point as Q, and then there is a diagonal between these 2 points, and that becomes the 2 points that you want to find, between which you want to find the distance in 3D space. Now as you can see, I will get two triangles over here. I have this triangle over here, and I can call this, for example, this point A, this point N, and I have this triangle on this face of the parallelepiped. I have this on the right face. I have this triangle ANQ, which is a right triangle. As you know, in a parallelepiped, all of these lines are perpendicular, mutually perpendicular. So this angle over here is a 90-degree angle. And moreover, this triangle is also a 90 degree, is a right triangle, because this angle is a 90-degree angle. And in case it's not easy for you to understand why this angle is a 90-degree angle, you see, you can, for example, go over here. You can always use this software for your personal use. If you are a student, if you're a researcher, or whatever it is that you do, if you basically for your personal use, for non-commercial use, you can always use this software. And well, of course, it helps a lot in basically looking at geometric figures and solids in 3D space. It has many different, the software has many different parts, and it essentially, it would take you some time to learn how to work with this software. They have a scientific calculator, there is a graphing calculator, there is geometry, there is 3D calculator, and so on and so forth. So you want to go to geogebra.org and work a little bit with this so that you get the hang of it. Of course, I don't really know exactly how to work with this. What I mean is that I'm not very fluent with GeoGebra, but sometimes, for example, simple things I can do with this, meaning that, for example, you see over here I have created a parallelepiped, which is a straightforward thing over here. You can, for example, what you can do, let me do this from scratch so you can see how I did this. And of course it took me, this is the graphing calculator, this is the geometry part, and so if you go to geogebra.org, they have all of these apps that they have created for mathematics. So you have the graphing calculator, which is basically just a grapher, like, for example, like desmos.com. You give it some equation and it will give you a graph. The geometry part is essentially is a great tool with which you can create all kinds of things related to, I think this is just related to 2D geometry, not 3D geometry. Meaning that, for example, you can go over here and create of course there is the option that you can show the axes, for example. You can show the axis here, and then there is show the grid, and then I don't know why they have no grid, major grids, major and minor grids, polar and isometric. So you can put the grids over here, and then you can also check this option over here, which says snap to grid. It will help you with, for example, suppose that you want to put a point over here. If you put the point over here, it will just snap to the intersection of the grids. That meaning that way you can make sure that you're exactly at the intersection of the two grids, and then you can put another point, for example, over here, and another point here and here, and that way now you can make sure that this is actually a square, for example. And then you can create a line segment over here like this and like that, and then you can now go and measure the angle over here. You see over here you can measure angle with given size, clockwise, counterclockwise, no. Now it used to work in a different way. Now they have changed it, apparently. Measure angle with, no. Here they have added this wasn't there a few months ago. I came over here, I had to do something in geometry, and this, for example, this option was not there. Now they have added this thing over here. Or area wasn't there really. They have added area as well. So for example, to measure this angle, you can, I suppose, use this over here, and then you can move this, even the label you can move, and you can see that this angle is 90 degrees. So that's how you kind of that's how you work with the geometry part. And there is point, basically line segment, there's polygon, circle with center, and then you can edit things here, you can construct things here, perpendicular bisector, parallel line, perpendicular line, midpoint, angle bisector, tangent, and then you can also go and do measure angles, measure distances, measure areas, and you can do, there are different types of lines over here, vectors and rays and lines and segment with given length. These come in pretty handy when you're working on something. These do come pretty handy. And then you have the circles, different kinds of, different things related to circles. For example, circle with center and radius, compass, semicircle, circular sector. You have some polygons over here. You can do some sort of transformations, and there is also media, image, and so on and so forth. There seems to be more here. There is a pen over here, freehand shape, relation, button, checkbox, input box. I don't know really what these do. Let me see. For example, if you go to the pen, you can write here something, which is, well, okay. And then you can create a shape over here. I don't know how anybody could use this kind of thing, but it might come in handy someday for you or for anybody. So this is the geometry part, and there is another thing over here called, they have the scientific calculator, which is apparently, you can change some preferences over here, rounding to 3 decimal places. You can go all the way up to 15 decimal places, or all the way up to 13 significant figures, font size, language, and then the keyboard is supposed to be there. And then you can have, I don't know, I don't really know how this works. There is a part in their website that says that teaches you how to work with this scientific calculator. That is also useful. these are really invaluable resources that we have today. Otherwise, like around 10 years ago, these kinds of things were just restricted to some, for example, to some very select computer-based algebra systems. And for those kinds of algebra systems, you had to pay, for example, back then, like 10-12 years ago, you had to pay like $5,000 or $4,000 for an algebra system, and you had to actually buy the whole software. There was still no subscription based. There was still no subscription around, so you had to buy the software. And there were all of these systems like the Mathematica, and there was something else also, and so you had to buy all of these. You had to buy all of these things, and these were not really accessible to anyone. Now these are freely accessible on the internet, which is pretty amazing, really. Now the part that we want to work with right now is basically the 3D calculator, and I think this is the beta version, as I'm not really sure, but I think it's the beta version. So what you want to do, and whatever you, now there is something over here that I will show you as well, which is pretty useful in many types of situations. So for example, I want to create that parallelepiped. So that parallelepiped, I go over here. So you see, there are two tabs over here. There is a calculator tab, and there is this tools tab. So if I go to the tools tab, and there is a more button over here, and there is all of these options over here available. And this is a 3D dimensional, it's a 3D coordinate system. Now you can see that right now my x's, these are my x's, these are my y's, and these are my z's. Okay, so for example, I don't exactly know how you would for example, if I wanted to put a point over here, right over here, in above this plane, somewhere over here in space, I don't know how I would do that. But I know that if I want to create, for example, a parallelepiped, which is what I want to do right now, I would go and choose cube, and then put 2 points over here, and then that would take care of the problem automatically. Then they create these points up here for you as well, and then you have a cube. Now I can go over here and basically choose the move option, and now I can move my cube in any direction that I want, which is an invaluable thing. It's an invaluable it's an invaluable possibility that you have, that you can actually create something and move it in space and look at it from different basically viewpoints. So now what I want to do, we want to connect basically this vertex to this vertex over here. So what I will do is that I will choose, there was something called segment, so I choose this segment I connect it to this segment, and also I connect these two vertices together. And so now if I go back and choose move here, you can see that there is a triangle over here on a plane inside this cube. Of course, this cube is a three-dimensional figure, but if you imagine that there is a plane at an angle of 45 degrees to this axis over here, on that plane there is a triangle inside this, or through this cube, which is basically this thing over here, this triangle. And of course, if you pay attention to basically the angle between this black line and this base of the triangle, you can easily see that this angle is actually a 90-degree angle. It is a 90-degree angle, as you can see. It is a 90-degree angle. But otherwise, using the figure that I've drawn over here, I tried to figure this out on my own, and well, I couldn't. I really could not. I really could not figure this out, and I couldn't see that the angle was actually a 90-degree angle because, well, I couldn't do it. I mean, anyway, I couldn't do it. So now that you know that you have a basically a 90-degree angle over here, and you have a right triangle over here, you have another right triangle over here, you can put together a couple of equations. Excuse me. You can put together a couple of equations and find the distance between the point P and the point Q. That's basically all about this situation. Now I'll take a few minutes rest and we will finish this together. Okay, so now basically in this triangle, basically you can say that since triangle APQ is a right triangle, you can write basically this is the hypotenuse of that triangle because it's in front of it's opposite the 90-degree angle. So then you can write PQ squared is equal to AQ squared plus AP squared. AQ squared plus AP squared. So that is in triangle APQ. Now in triangle ANQ, so now in triangle ANQ, this is also a right triangle. So and AQ is the hypotenuse, so you can write basically AQ squared is equal to AN squared plus NQ squared. AN squared plus NQ squared. So as you can see, AQ squared over here is equal to this expression, and so if I call this equation number 1 and if I call this equation number 2, then based on equation number 2 I can write equation number 1 as PQ squared is equal to AQ squared, which is equal to this AN squared plus NQ squared plus AP squared Now these points over here, this distance AN is equal to, you see that the point is on a plane basically parallel to the XY plane. So that means that the z coordinate, that means that the z's over here are the same. So Well, if I imagine that this plane, that basically AP, basically the bottom side, the bottom face of this parallelepiped is it doesn't really have to be exactly on the XY plane. It could be above the XY plane, but of course the Z coordinate of these 2 points, the Z coordinate of these 2 points A and N are the same. So that and of course you see that the Y coordinate of these 2 points are also the same. They are basically they are along the same line, and for example you could trace them back to a single Y on the Y-axis. So the Z's are the same, the Y's are the same, so the only difference that there is here is the difference in the X coordinate of these 2 points. So then I can write the distance between A and N would be x2 minus x1. Now NQ is equal to basically the distance between N and Q, and over here you can see that the difference between the difference between these 2 points is in the Z coordinate of the 2 points, meaning that the X's are the same, the Y's are the same, but the Z's are different. So that you could write this as Z2 minus Z1. And AP you can write it as basically over here you can see that the difference is in the Y coordinate of the 2 points. The X coordinates of the 2 points are the same. The X coordinate of the 2 points are the same. The Z coordinate of the 2 points are the same. The only difference is between the Y coordinate of the 2 points. So then over here I can write y2 minus y1, and now this equation I can write it as pq squared, and pq squared, as you can see, is actually the distance between the 2 points that we were looking for, and these are 2 points in three-dimensional space. And now we have found that in terms of x1 y2, z1 z2, and y1 y2. So if I add basically this whole thing together, pq squared, so an squared would be this thing, x2 minus x1, this expression whole squared, plus nq squared, which is z2 minus z1 whole squared, plus ap squared, which is y2 minus y1 whole squared. So I write y2 minus y1 whole squared plus z2 minus z1 whole squared. And so PQ then would be the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared, and that is basically the whole story here. So that means that if you have any 2 points P with coordinates x1, y1, z1, and another point Q, for example, with coordinates x2, y2, z2, then the distance of these 2 points in three-dimensional space is given by this equation, x2 minus x1 whole squared, y2 minus the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared. And if you compare this equation to the basically distance formula that we had before for two-dimensional space, it was x2 minus x1 whole squared plus y2 minus y1 whole squared. That is for 2D space, and the only thing that has been added is the z coordinate of the 2 points. That's basically all there is to this formula. Of course, now there is of course this is pretty valuable over here. Let's talk about this as well. It says that in particular if x1 is equal to y1 is equal to z1 is equal to 0, then that is the point P is the origin. That is the point P. The point P is the origin. Is the origin O. Then basically OQ is equal to, so in this formula, if x1 comma y1 comma z1 is equal to 0 comma 0 comma 0, then in this formula you will have basically this becomes OQ. It would be the square root of x2 squared plus y2 squared plus z2 squared, and x2 squared plus y2 squared plus z2 squared, which gives the distance between the origin, and it's this basically which gives the distance between the origin O and any point x2 comma y2 comma z2. So that means that if you take the coordinates of that point as simply as x comma y comma z, then the distance of that point from the origin is going to be the square root of the distance of that point from the origin is going to be, for example, OQ, simply x squared plus y squared plus z squared, which is basically the same thing that we had in this case of 2D distances. In the case of 2D distances OA, the distance from the origin from any point A in 2D space was the square root of x squared plus y squared. We use this a lot in figuring out some equations for parabolas, for hyperbolas, for the square, for the circle, for the ellipse, and so on and so forth. So now we have a couple of examples here, and we are basically, so let's go through these examples one by one. Okay, so now let's do a couple of examples. For example, you want to find the distance between 2 points P and Q. Let's say that let's say that your the points are basically p's with coordinates 1, -3, 1, -3, so 1, -3, comma 4. And as you know, this point is basically your x is positive, your y is negative, and your z is positive. So you are on the top of the coordinate axis 1, 2, 3, 4. So you are at in the 4th octant, up here basically. You are somewhere over here, not somewhere, but exactly in the 4th octant. So this is 1st, 2nd, 3rd, and 4th octant over here, for example. Over here you can see that your x's are positive, your z's are positive, and y's are negative. And here y is negative, both of these are positive. So try to imagine these in your mind until you are comfortable with the points, until you know where they are pretty comfortably, because these skills have to be developed starting from here. You need to be able to see things in your mind in a three-dimensional way. That is what you need to, that is the kind of skill that you need to cultivate starting from here basically. Otherwise you would have to depend on three-dimensional software all the time, which is of course sometimes necessary or unavoidable, but simple things like these you can always do in your mind. And your point Q is basically -4, 1, 2. -4, 1, 2. This point is your x is negative and both y is then positive. X is negative, y is positive, and z is positive. You are in the 2nd octant, for example, here. So what that means is that then your PQ, distance between P and Q, is x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared. And so what this is equal to, basically x2 minus x1, which is, take this as point, for example, 2 and 1. So -4, -1 whole squared plus y2 minus y1, 1 plus 3 whole squared, 1 plus 3 whole squared, and 2 minus 4 whole squared. And this is equal to the square root of -5 squared plus 4 squared plus -2 squared, and that is equal to the square root of 25 plus 16 plus 4 plus 4, that's the square root of 45. The square root of 45 units, which is basically 9 times 5, so that's 3 times the square root of 5 units.